Okay, so the intro to the Mealy machine is really short, even shorter than it was for the Moore machine. So the only difference, we had to, going from counters to the general Moore machine had a couple new pieces, but the difference between a Moore machine and a Mealy machine is purely in the rules that are applied to any final output results in a Mealy versus a Moore machine. So in the Moore machine, the output was allowed to be a function of only the present state, the Q values. In a Mealy machine, and by extension that means it was banned, the output is banned from observing the input directly, which is the only reason this logic is separate from this logic, because the JKDT is controlled by the present values, the present state, and the input, while the output was allowed only to be a function of the present state. But in the Mealy machine, the output is now allowed to observe the input directly. Oops, that's not going to fit. And so then, just do this. The output comes just from the main combinational logic. The output is now allowed to observe X itself as well. So the output comes from just one big combinational logic block. So now the output is also allowed to observe X, so there's no reason to draw it as a separate box. But that's it. That's the only difference really between the Moore and Mealy machine. Although that does create a number of interesting details. But that's it for the modifications. Now I'm going to continue with this particular example in the Mealy machine. So I've pulled up the Mealy sequence detector version here. I lost a little bit of the color that I had updated a little bit later, but that's all right. So the difference with the Mealy machine is that we will not need a dedicated state for when our sequence is 0, 1, 1, 1, 0, 0. We are going to be able to produce a 1 in a Mealy machine slightly differently. Because the Mealy machine can observe the input as well, we will output a 1 while in F, the input is a 0. And then on our way out of F to the next state we go to, we will output a 1 as we move from F to the next state when we're in F and a 0 is the input. When we clock it, that 0 gets locked in and we advance to the next state. During the advancing to the next state, we just output a 1. And we don't have to output a 1 by sitting in a state G. We can output it as we travel from F to another state, which frees us up from having to define a G state. Now, so we still need the criteria for the last 5, the last 4, the last 3, the last 2, the last 1. And as a result, everything is basically the same while we're in A, B, C, D, and E. Nothing has changed about the sequence we're trying to find or about how close we are at each given step. So in A, B, C, D, E, and F, nothing has actually changed except our output is now drawn on the arrow instead of inside the bubble, because in the Moore machine, the output was a function only of the present state and thus could be written inside of the bubble because all the information needed to get it is right there. But in the Mealy machine, because the input is also involved in addition to the present state, the output is placed on the arrows along with the input. So just like in this diagram, on A0, A is going to go to B, but while it does so, the sequence is incomplete, so we output a 0, and this is just a slash. And then from B to C, we advance on a 1, but that doesn't complete the sequence. C to D on a 1 does not complete the sequence. D to E on a 0 does not complete the sequence, and E to F, also on a 0, does not complete the sequence. Now, from F, if we get a 0, wait, sorry, I messed this up. Right, okay, so sorry, I messed up this piece right here. So it's supposed to be on a 1, we go to E. Yeah. Okay, so I'll fix that. Sorry, in E, on a 1, we advance, sorry, in D, on a 1, we advance to E. E, on a 0, advances to F, but outputs a 0. So then if we're in F and we get a 0, we're going to go somewhere, and while we do it, we're going to output a 1. So we'll put a pin in that for the moment. But I also want to finish up the rest of the arrows in A. So just like before, in A on a 1, for the same reasons it did in the Moore machine, we return back to A on a 1, and B, when it gets a 0, it goes back to itself, and that doesn't complete the sequence, so we output a 0 when we do. C, sorry, so this B is, it's a 1, 0 for B, so let me drag it closer to the B arrow there. Yeah, and I'll redraw the line. Okay, and then, so C on a 0 returned to B was what we determined in the Moore machine. In D on a 0, that also took us back to B. So, and we output a 0 while we do that. In E, on a 1, it took us all the way back to A, because nothing's different about the sequence that we're observing as we do all of these things. But here in F, things are slightly different. So, if we are in F, in order to be there, we have to have observed 0, 1, 1, 1, 0. If we get a 0, that will complete our sequence. We'll have a 0 to end it out, and we would go 0, 1, 1, 1, 0, 0. So in F, on a 0, we are going to output a 1. And if we're in F and we get a 1, we would get 0, 1, 1, 1, 0, 1 as a result of where we started with the additional 1 added on. We would not complete the sequence, and we would have to output a 0. But we need to determine, slightly differently this time, where are we going out of F as we output that value. And to do that, we have to check the 5 criteria that we have here. So if you look at on a 0, we would get the complete sequence, but we need to keep track of how close we are for next time. So if we get a 0, we complete our sequence, and then we have to inspect the last 5. So there's a 1 here, and the last 5 needs a 0 there to match, so we fail that one. If we check the last 4, 0, 1, 1, 1 is not the same as 1, 1, 0, 0, so we fail that. 0, 1, 1 is not the last 3, so we fail this. 0, 1 is not the last 2, so we fail this, but the last one is a 0, so we still meet the criterion for being in B if an additional 0 is dropped in after F. So we would meet the criteria for being in B, but we output a 1 as we go there. So in F, on a 0, we output a 1 for completing the sequence, and we travel to B to line us up, because that 0 can be used as the first 0 in a new round of the sequence. We're 5 steps away, a 1, 1, 1, 0, 0. And then the other option, the one that doesn't make progress in F, would be where we get a 1. To be in F, we have to have had 0, 1, 1, 1, 0. 0, 1, 1, 1, 0. And then if we put a 1 in there, now we have to check our criteria. So the last 5 do not match those 5. The last 4, 1, 1, 0, 1, do not match that. The last 3, 1, 0, 1, do not match that. The last 2, however, 0, 1, do match our 2 criterion here, and so we do meet the criteria to enter state C. And I'm running out of space there, but we can go to C. Oh, this is the one that should have gone. Yeah, I'm going to cross either way, so I may as well just... Sorry, I'm going to swap this out real quick. So this one, I'm going to make this arrow the 0, 1 that travels to B. And then I'm going to erase this, just to make it a little neater. Okay, because that one's supposed to go to C, so I'll just clear it back to there. Okay, so that was the 0, 1. I'm changing this one to be the F on a 1 arrow. So in F on a 1, we would not complete the sequence, so we output a 0 right there. But our destination would be C on a 1. We would not complete the sequence, but we would have had a 0 followed by a 1, which is why we're allowed to be in C. The only way to go to C is if we had a 0 followed by a 1, and if we've drawn this accurately, there is no way to get there other than through that path. So a 0, 1 from F, 0, 1 would get us there that way, and in F, if we get a... to be in F, we have to have gotten a 0 from E, so then the 0 from E, then the additional 1 also takes us to C. Again, a 0, 1. As long as we're careful, no matter which of these we're coming from, in D, on a 0, we go to B, and then the 1 would take us to C, and all of that's good. So this would be the Mealy machine diagram. We've eliminated the dedicated G state, and our 6-digit criterion is then unnecessary. But by doing the 5 remaining criteria and then choosing our output based on the present state as well as the input coming in, we now get an output that as we leave F traveling to B, because of this 0, we output a 1 as we make that move. And so we can follow this diagram. It's the same thing again. So all we have to do, I'm going to use this table again. So I've changed G to a does not exist. And then we have A, B, C, D, E, F. So if we get a 0, our new destinations are written in this table here. So our new destinations would be these. Oh, I wanted to paste them as data. Then because these are do not exist, so are these and these. Our destinations on a, well, okay, actually. So I pasted our destinations for A through F on a 0. And then we also have these outputs that are now a function of the input and the present state. So this set of outputs is associated with these states on this input. So they would go in that order. And then these are the same states on a 1, output slightly differently. They output like this. And then these would be don't cares because it doesn't matter because we're never going to enter those states. So those are our outputs. Before, the output depended only on the present state, but now in the Mealy machine, it depends on the present state and the input that we get. So that's why we have two separate outputs here. We drop those in there. We have that set of destinations. This was the set of destinations on a 1. So we'll paste them in there. Okay. Now it's just a matter of getting our codes. So I'm going to center these, because it'll make it a little bit neater. Come on. Center, center. Oh, okay. Yeah. Right, so now it's just a matter of pasting the relevant codes. So this is the A code. So all of the A's get that code. This is the B code. B. So everywhere that there is B, we paste that in. This is the C code. We have a few of those. We can go to C here and here. There's going to be at least one D, but probably exactly one. So there's one there. As you advance, there's going to be fewer and fewer. The early ones there's several of, and the later ones there's only ever going to be one of, pretty much. So that's the E code. E is where we go here, and this is the F code. The destination F is that spot right there. These do not exist are we don't care where they go because we never enter them. And again, what's nice with D flip-flops is we can just copy and paste the next states over. And so this is buildable in Logisim with the same tricks as before. So just like before, we set up our inputs X, Q2, Q1, Q0. Our outputs Z, D2, D1, D0. So now it's just a matter of pasting Z, D2, D1, D0 into this, if we're going to have Logisim do it, which is fine on the project. But I want to move quickly through this because we covered it in the counter video there. And so now it's just a matter of building that circuit. So the circuit name is Mealy 011100. And so just like before, we're going to drop some D flip-flops in there. No big deal. There's D0, there's D1, there's D2. Q0 swings around. Q1 swings around. Q2, swing that around. So there's our X, there's our Z. We'll drop a clock in here. All right, so it's going to be one tricky bit that happens when we do our Mealy machine. So just as before, our critical code is 0, 1, 1. Here's a 0, but uh-oh, I messed something up, didn't I? 1 second. Okay, I have no idea what I did. It was fine this time. So we go 0, 1, 1, 1, 0. Notice, though, that we're supposed to need a 6th 0. And as x wobbles around, so does z. So this is a fundamental thing that the Mealy machine does. Because the output is a function of not just the present state, but also the input, what the Mealy machine output shows is slightly different than the Moore machine. The Moore machine only displays a 1 when the final 0 is clocked in. We would say that the Moore machine output is synchronized as a result of being a function of these synchronous flip-flops. But the input is not a synchronized value. It's allowed to wobble whenever it wants. And so because z pays attention to x, it changes when x does sometimes. So it's important that whatever looks at the Mealy machine needs to keep in mind when the Mealy machine output is valid. With the Moore machine, the output is valid at all times. It only shows the 1 when the final 0 is clocked in, and continues to show it until an additional digit is clocked in after that. But the Mealy machine is always telling you what the output should be if you trigger the clock in that moment. So this output is only valid at the instant this clock rises again. When this clock rises, this input is locked, and the z is responding to the true, consistent, synchronized input, the final 0. So depending on your device, if the thing that looks at the Mealy machine is clocked, then the thing that looks at the Mealy machine will only be paying attention to this output when the clock triggers. And there are circuits like that only do things on the clock edge and will wait to do anything with this 1 until this clock triggers. It observes the same clock and knows when this z is valid. For us, we can't watch the clock at the same time as we watch the output. So in the moment that I click this thing is valid and then no further. So as soon as I click this is going to change. And our human eyes can't jump from the clock to the z fast enough. And some circuits can only observe they're not synchronized to the clock, and they're always staring at this z. So for circuits like that, and for eyes like ours, we need the assistance of a simple circuit who acts as a clock signal watcher. And so the simple circuit which will do this is a D flip-flop. So you just hand the D flip-flop the clock you want it to observe, and hand it the Mealy machine output, and then I like to call this the Z sync. And so this is synchronized to the clock. So this D flip-flop is sitting here watching this, and it's just waiting. As soon as the clock triggers, the D flip-flop says, output is valid, I'm going to kick it to my output, and I'm going to keep it there until a new data bit is clocked in. So this will make it consistent with the Moore machine and only produce the final synchronized one when the final 0 is clocked in, and it will hold it until a new digit enters. So now we can watch the full process: 0, 1, 1, 1, 0, and only on the 6th bit, being a 0, does this clock watching D flip-flop confirm the accuracy of the 1 and display it until a 7th digit is plugged in. So that's an important detail with the Mealy machine, but that's it for what was important in the Mealy machine. So I hope you're having a good evening, and if you're still working on the Moore Mealy project, or if you want to revise it after seeing this video because now it clicks, you can feel free to resubmit after. Because of the way this went down, you can resubmit it Because yeah, you should be allowed to have feedback. So yeah, if you watch this video and it helps, just write me a note. You can resubmit it and write in the comments there that it made more sense after the video and you were able to adjust it. So I will be grading those very soon. So this was the last video I wanted to record. And so if this is still the term that I made this video, I'm grading as many papers as I can now for the rest of the evening. Yeah, so we'll see you during the final exam. So if everything's going well, have a good day.